Hello everyone, and welcome to Recitation 0 Part B, Fundamentals of Numpy and Pytorch. As a reminder, this is the second of 6 Recitation 0 videos which you'll find on the course website. I encourage you to watch them all. They've been very carefully planned out to help you get acquainted with the basic skills required for your success in deep learning as well as in this course. This recitation in specific will be going over Numpy and Pytorch, which both have very similar operations, but I'll try my best to point out the differences as we go along. This recitation will also be very helpful for Homework 0 Part 1, where you'll get to practice different data processing techniques as well as revise some mathematical operations. Now let's go over the contents. First, we'll start off with setting up Numpy and Pytorch, installation, importing, and so on. Then we'll learn how to initialize arrays and tensors, and access and modify data. Then we'll move on to different techniques to pivot and combine data, and finally we'll end off with mathematical operations. A quick note before I get started is that you'll find a link to this notebook down below in the comments, so feel free to pull it up and try things along as we move. In order to make sure that you're ready to go ahead and run this command on your machine to make sure that you already have Numpy. If you don't already have it, you can go ahead and run this command to install it. Once it's installed, go ahead and import it to make sure that everything is ready to go. Same thing goes for Pytorch. Now moving on to initializing arrays and tensors. There are many ways to initialize an array or a tensor. First way is to initialize an empty array of zeros or ones. The only thing you have to specify here is the size of the array. And make note that you must put the size inside of a tuple. Over here, I'm initializing an array that is 4 rows and 3 columns. Over here, I'm initializing another array of the same size, except this one is full of ones. I can also have it be 3-dimensional. In this case, I've added a 5 here. I can also initialize a random Numpy array with uniformly distributed numbers from the standard normal distribution, as I've done over here, and it's shown over here. I can also initialize a random Numpy array with randomly distributed integers in the range that I specify over here. In this case, I want to initialize the array with integers from 0 to 3, not including 3, which gives us the array down here. Moving on to torch tensors, it's very similar. In this case, just the syntax is different, so I've specified this size to be 5 rows and 3 columns, and I'm initializing a tensor of zeros. Over here, I'm initializing a tensor of the same size, except it's with ones, and you can see the output over here. I can also initialize tensors in different ways. Over here, I can return a 2D tensor with ones on the diagonal and zeros elsewhere, as I've done in the third tensor right here. I can also initialize a tensor with random numbers from a uniform distribution in the interval 0 to 1, as is shown over here. The last way is that I can initialize a 1-dimensional tensor, and here note that it can only be 1-dimensional with values from the interval that I've specified as well as a step. So over here, I've asked it to return a tensor that has numbers starting from -3, ending with but not including 9, and steps of 2. So you can see that this is the tensor that I've gotten over here. Moving on to interconversions, a lot of the time we may have an existing data structure that we just want to convert to an array or to a tensor, so this is very useful for that. First thing, we can look at how to convert a list to a Numpy array, as I've done so over here. We start off with a list and we end up with an array. I can do the same thing for a tensor. I can start off with a list over here and end up with an array. And here I've printed the type so you can see that obviously. Another thing we can do is convert between arrays and tensors. So over here I've demonstrated how you can convert from an array to a tensor, as you can see over here, and vice versa from a tensor to an array. Moving on, we need to be able to slice and index our data, and over here I've shown different ways you can do that using both Numpy and Pytorch. It's quite similar to how you'd usually slice a normal list in Python, so it shouldn't be very hard. I've just shown some examples of different ways you can index an array, and the exactly same way you can do that with a tensor. Alright, now moving on to pivoting data. Before we get started, there are some keywords you should know. When we're talking about the size and the shape of the data, we mean the same thing. This is important for multiple reasons. First thing, we need to be able to know the rank of our array or our tensor. And knowing the shape gives us that. Basically, the rank of an array or a tensor is the length of its shape. For example, if I have an array of size 3, 4, that means it's in the second rank. If I have an array of size 3, 4, 5, it's in the third rank. The second reason it's important to know the shape of your data is to be able to know the number of elements. The number of elements is just the product of the shape components values, and this is very important for reshaping or using any operation on this data, because we always must account for the data, because what we want to do is change the shape and not the data. So first off, let's start with flattening. A flatten operation on an array or tensor reshapes the array or tensor to have a shape that is equal to the number of elements contained in the array or tensor. This means that we remove all dimensions except for one, so it's quite literally flattening the data. As you can see over here, I've initialized an empty array with random integers, and I've given it this size. So over here it's printed, and then I've performed the flatten operation, and you can see the result over here. It's been converted to a single dimension, and you can also see that it has the same number of elements, 2 times 3 times 4, which is 24. The same thing goes for torch tensors. So here we've initialized a torch tensor with the same size, and when we flatten it, we've also got 24. The second operation we'll talk about today is squeezing. So squeeze and unsqueeze go hand in hand. What squeeze does is it removes the dimension that has a length of 1. So over here, I've initialized a Numpy array that has 1 as one of its dimensions, and as you can see, that's kind of redundant over here. It might be useful in some cases, but over here you can see that there's one dimension that just has a length of 1. So what squeeze does is it removes that. Over here was specified the axes, but you wouldn't need to if it's just one. If it's just one axis that needs to be squeezed. Over here, we've performed the opposite of that operation. We've unsqueezed, and here we've specified the axes, and as you can see, this is the original array, this is the squeezed version of the array, and this is the unsqueezed version of the squeezed version, which is basically taking it back to the original. The same thing can also be done with torch. So as you can see, this is the original, this is the squeezed, and then this is the unsqueezed. Note that in all situations we go back to the original shape. Now let's move on to the third operation we have today, which is the reshape operation. What this operation does, as its name, it flattens the data you have and it restructures it into the new shape that you specify. Over here we have the original array has the shape of 2, 3, 4, but we want to change that into 4, 2, 3 or 6, 4. The important thing to notice here is that all the new shape must account for the number of elements in that tensor or array. What that means practically is that the product of the size values should be the same across from the original to the new shape. So as you can see here, 2 times 3 times 4 is the same as 4 times 2 times 3 is also the same as 6 times 4. So as you can see, here's our original array, which has the size of 2, 3, 4. We've reshaped it here to have the size 4, 2, 3, and over here we've reshaped it once again to have the size 6, 4. The same exact thing can be done with torch tensors. We start off with an array shaped 3, 1, 2, 2 to shape 3, 4, 1 to shape 2, 6, and as always, the product of the size components should always be the same. The important thing to note here is that reshaping is how you can move between ranks. So we started off with a tensor of rank 4 to a tensor of rank 3 and then to a tensor of rank 2. A special case you might want to be aware of is using -1 as one of the shape parameters. What this does is that we simply don't know the dimension here and we want Numpy and Pytorch to figure it out. How they will do this is how any of us would do this. Would look at the length of the array and the remaining dimensions and make sure it satisfies the total number of elements. So over here, this is our original array once again, 2, 3, 4. We want to reshape it to have size 4, 3, and obviously here we can see that the missing size is 2, which Numpy figures out. So here's our original array, 2, 3, 4. Here is our reshaped array, 4, 2, 3. Over here, we've reshaped it down to one-dimensional and we've put -1. So Numpy automatically infers that the missing size is 24, as we've shown here. Same exact thing can be done with Pytorch, which I've demonstrated over here. We start off with 3, 2, 1, 2. We want to reshape it to 3, -1, 1. and we can easily infer that the missing size is 4 here, which Torch automatically infers. We can also reshape it down to one-dimensional using the -1, and over here we can see that the missing value was 12. So basically, reshaping with -1 essentially does the same thing as flatten. The last operation we'll discuss in this section of pivoting data is a transpose operation, and this is where Numpy and Pytorch differ quite considerably in the syntax. To start off, I've initialized a Numpy array over here of size 2, 3, and it's printed out here. What I want to do is transpose that, and that's how normal matrix transposition occurs, as done so over here. Over here, I've left the axes empty, the axes parameter empty, it's not shown over here, and so it just, this is because it's two-dimensional. What I can also do is transpose particular axes. So as you can see here, the axes parameter has a size, a tuple. The tuple must be the size of the rank of the array. As you see over here, I've initialized an array of rank 3. So the tuple over here must be of rank 3. What this tuple represents is how the axes in the new array will look like based on the axes of the old array. So over here, in position 0, I have axes 0. In position 1, I have axes 1. In position 2, I have axes 2. What this does is it doesn't change anything because I've set up the axes to be exactly the same axes as the original array. So, as you can see here, this is the example array with positive numbers up here and negative numbers up here. And when I transpose it using 0, 1, 2, it stays exactly the same. Things change when I start switching around. So over here, in place of axes 0, I put axis 1 of the old array. And in place of axes 1, I've put axes 0. So what I've done here is essentially switched axes, transposed axes 0 and 1. Over here, I've transposed axes 2 and 0. And and in the last two examples, I've tried different combinations. So as you can see here, this is the transposed array with these axes, and over here as well, and over here as well. In Torch, the syntax is a little bit different. So using the actual transpose operation, you can only switch 2 dimensions. So over here, I've created a tensor with size 2, 3. And when using the transpose operation, I can only specify 2 axes that are to be transposed, and I cannot leave it empty. So over here, I'm switching axes 0 and 1, which would be exactly the same as switching 1 and 0. So as you can see here, this is my original tensor, and this is the transposed version of that tensor. Over here, I've also shown different examples of how to transpose another tensor, as shown here. Now, to be able to switch more than one axis at the same time or specify which axes to be changed, you use the permute operation, which is shown over here. So as you can see here, I'm switching, this is the exact same thing, so I'm not changing anything. 0, 1, 2 is shown in the example in Numpy above. And over here, I'm switching it to be 1, 0, 2 and 1, 2, 0. If you follow along, you can see that I've tried to match the Numpy and Pytorch examples. So if you go ahead and look at the example numbers between Torch and Numpy, you should be able to see that they correspond, so you can compare how things are done in both. Moving on to section 5, over here we'll be looking at different methods to combine data in arrays and tensors. So the first one we'll look at is concatenation. So what a concatenation operation does is that it joins a sequence of arrays or tensors along an existing axis. And this is something that's important to note to differentiate it from the next operation we'll talk about. All arrays or tensors must either have the same shape except in the concatenation dimension or be empty. So over here, I've initialized 2 random arrays of the same size exactly. I could have shown you like different sizes, but since I'm going to be showing you examples of concatenation on all 3 axes, I kept them the same. As you can see here, this is our original array with dimensions 3, 4, 5. This is our second array, and when we concatenate them both, you can have a look at. So this is concatenation along axis 0. This is concatenation along axis 1. And this is concatenation across axis 3. So the thing to note here is that the resulting array, we add the size in the axes that we're concatenating on. So we started off with 3, 4, 5 and 3, 4, 5. When we concatenated on axis 0, we ended up with 6, 4, 5. When we concatenated on axis 1, we ended up with 385. And when we concatenated on axis 2, we ended up with 3410. The same exact thing can be done in Torch, obviously with the difference in the syntax. So the same thing here. This is our first tensor, 345, second tensor, 345, concatenation along axis 0, concatenation across axis 1 and axis 2. Moving on to our second operation of this section, stacking. So stacking operation joins a sequence of array or tensors along a new axis. The axis parameter specifies the index of the new axis in the dimension. In this scenario, all arrays or tensors have to be the same size, and the resulting array or tensor has one more dimension, so the rank increases by 1. So as you can see here, I've initialized the same random arrays, 345 and 345. I'm stacking them in axis 0, 1, 2. So one thing to note here is that stacking on axis -1 essentially tacks on another dimension at the end, so it's not the same as the previous example, so that's something that I realized was incorrect, and I went back and I edited it in the notebook. So let's have a look. This is our first array with dimension 345. Our second array also dimensions 345. So when we stack them, they're not concatenated because here we've added a dimension. So as you can see here in axis 0, we've added a new dimension, and it has a size of 2 since we're stacking 2 arrays. So the new size is 2, 3, 4, 5. When we stack it along dimension 1, so over here it's 3, 2, 4, 5, so the 2 has been added here because we're stacking 2 arrays in axis 1, so it's in position 1. Lastly, we stack it over here in axis 2, so the resulting size is 3, 4, 2, 5. So once again, we're stacking 2 arrays and in axis 2. Finally, when we stack onto axes equals -1, we create a dimension at the very end. So as you can see here, the dimension is 3, 4, 5, 2. Once again, the 2 is because we're stacking 2 arrays, and it's in the last axis position because we specified axes equals -1. The same exact thing can be done with Torch. Once again, we specify the tensors we want to stack, and we specify the dimension. Over here, when we specify dimension equals -1, it's tacked on to the end. We can see that over here. The original tensors are 3, 4, 5, 3, 4, 5. And when stacked in dimension 0, we end up with a size of tensor 2, 3, 4, 5. Stacking on dimension 1 makes it 3, 2, 4, 5. Stacking on dimension 2 makes it 3, 4, 2, 5. And finally, stacking with dimension equals -1 makes it 3, 4, 5, 2. The third operation we're going to talk about in this section is the repeat operation. So this does exactly what the name suggests it does. It repeats particular elements of an array. So starting with Numpy as usual, here's our original array with dimensions 2, 2. When we repeat and we mention that we want it repeated twice, this is how it's repeated. When we specify the number of repeats and the axes, so over here we specified that we want 3 repeats along axis 0. This is what we end up with. We end up with 3 times the first element and 3 times the second element along axis 0. Over here we've mentioned we want it along axis 1. So once again, here it is. And when we place the size inside of an array, we're specifying which elements we want to repeat how many times. So over here for number 4, we've requested that the first element is repeated twice, as specified here, and the second element is repeated 3 times. So the dimensions change accordingly. In Torch, we can do the exact same thing. However, we cannot specify which dimension along which we want the repeat to occur. So using the repeat function, it automatically repeats it along all axes, as you can see here. But we can use the repeat interleave function, which helps us specify which dimensions we want it to be repeated on. This will be particularly useful for homework for part 2. Finally, we move on to padding, which is the last part of this section. Arrays and tensors need to be padded to ensure that computations can be optimized by transforming the underlying data to become of the same size. So sometimes you have some data that's a particular shape but you don't want to lose data and you don't want to lose the structure of the data. So you want to add things to the sides or the top or bottom of the array just to make it a particular shape. That's called padding. So here's our original array. I am setting up the width of the padding, padding to the left, right, top, and bottom, since this is just a 2D array. It doesn't have to be just two-dimensional, but this is the example we have here. Over here, I'm using the same command 4 times, but with different modes, so you can see the difference. So over here, the first padded array, I've specified the mode to be constant. You can also change the value for it to pad with. So over here, we've specified pad left to be 1, and we've added an entire column of zeros. Pad top is also 1, so this is 1 row of zeros. Pad right and bottom are 2, so we have 2 rows and 2 columns of zeros. And obviously the dimensions change along with that. When we specify the mode to be edge, it just copies whatever values it finds on that edge when it's padding. Over here, we have the mode set to be reflect. So when we go down to the third example, we can see that it's been reflected with the width and dimensions we've specified. Last but not least, we've specified the mode to be symmetric. So over here, you can see that's how it's been done over here. Padding with torch is very similar. You can also try playing around with the modes from over here. One thing to note when padding is that there's a big difference there's a slight difference in the syntax. So just keep in mind that over here, when you're specifying the padding widths, it's left, right, top, bottom, and it's in a single tuple. With Numpy, it's top, bottom, left, right, and it's in like a double tuple. So just keep that in mind when you're using these functions. Last but not least, we'll go over some mathematical operations that you can do with Numpy and torch arrays and tensors. So the first thing is pointwise operations. So we've initialized 5 arrays with different shapes here. I'll show you that you can add with scalars, multiply with scalars, element-wise addition, element-wise multiplication, which is also called the Hadamard product. You can also do things like finding the absolute value and using different functions, as well as adding between different sizes. So over here you can see the examples, and you can try and match the examples with the specified thing. Moving on to torch, you can do the exact same operations once again. You can also do some reduction operations, such as the sum, mean, maximum, minimum, argmax, and so on. So here I've just shown some examples. You can specify the axes along which you want the operation to be performed, and same with torch. You can also perform various comparison operations between arrays and tensors. For example, greater than, testing if 2 arrays are equal. You can also perform these along particular axes. So in these examples, you can see that. The same thing can also be done in torch. Last but not least, we're going to go over some matrix operations. So just as a quick revision, this is just an example for matrix multiplication. Over here, I've added examples for vector multiplication, matrix vector, and matrix multiplication. As you can see here, there are 2 ways to multiply a matrix and a vector. So there you can use the dot matmul operation, or you can use this @ sign. Moving forward with torch, you can also do the same thing. However, you can only use the torch.matmul operation. Lastly, these are 3 matrix operations that you might find useful later on during the course. The first is the dot product, which is also known as the inner product, which is involved in matrix multiplication. The second is the tensor product, which sums the products of elements from 2 matrices over indices specified by a set of axes. Please have a look at this link for more information about that. Lastly, there is einsum, which performs a multitude of different operations on matrix and is also very useful, so please have a look at this link. I've provided examples of both, so of all 3 for both Numpy and Pytorch. So, for example, I've set up 2 matrices here. You can perform the dot product between them. You can also do it between 2 vectors. For tensor dot, you can also perform it between 2 arrays, as I've shown here. And also with INSIM, same thing. You perform it between two matrices. So INSIM is just basically another way to multiply two matrices, but be careful how you specify the indices because they represent the shape of the new matrix. So please go ahead and play around with these and see the kind of shapes and results you produce. And here's the same thing done once again with Torch. However, just keep in mind that for the dot product, you can only do it using one-dimensional vectors for Pytorch. That's it for me today. Thank you for listening and best of luck on the course.